The Russky Island Bridge, also known as the bridge over the eastern Bosphorus Strait in Vladivostok, is a remarkable engineering feat that stands as one of the longest cable-stayed bridges in the world. It was built as a part of a federal initiative to transform Vladivostok into a hub of international cooperation in the Asia-Pacific region. The project, initiated in 2008, was completed just in time for the Asia-Pacific Economic Cooperation (APEC) Summit in 2012. The bridge connects the mainland of Vladivostok to Russky Island, significantly enhancing the region's transportation infrastructure and serving as a new landmark for the city. The Russky Island Bridge is a significant component of the Primorsky Krai region's transportation network, providing a vital link between Vladivostok's mainland and the island. Before the bridge's construction, access to Russky Island was limited and primarily dependent on ferries. The completion of this bridge has greatly improved accessibility and has spurred development on the island, which is home to the Far Eastern Federal University and various research institutions. Built under the federal program aimed at boosting Vladivostok's status as a center for international cooperation, the bridge reflects the city's ambitions to emerge as a key player in the Asia-Pacific. The choice to build such a massive structure was driven not only by the need for improved connectivity, but also to leave a lasting impression, establishing Vladivostok as a city of global significance. The bridge's design had to account for challenging environmental conditions. The eastern Bosphorus Strait, which separates Russky Island from the mainland, is roughly 1.5 kilometers wide at the bridge's location. The area experiences extreme weather, including winds up to 36 meters per second, 6-meter-high storm waves, and winter temperatures that can drop below -30 degrees Celsius. The bridge was thus designed to endure these harsh conditions, withstanding strong winds, storm surges, and ice thickness up to 70 centimeters. The structure is unique in its dimensions, featuring a central span of 1,104 meters, which made it the world's longest cable-stayed span at the time of its completion. The pylons that support the bridge stand 320 meters tall, making them some of the tallest in the world, and the stay cables reach lengths of up to 580 meters. These cables are composed of galvanized steel wires, ensuring a high degree of strength, durability, and resistance to corrosion, with a design service life of over 100 years. The construction of the bridge was a monumental task, completed within a record time of 43 months. The project involved the development of new production facilities on the Nazimov Peninsula and Russky Island to support the construction. These facilities included rebar welding workshops, laboratories, woodworking shops, mechanical workshops, and state-of-the-art concrete mixing plants. One of the key innovations used during construction was the deployment of reverse circulation drilling rigs, which were utilized in bridge building in Russia for the first time. A total of 20 advanced drilling units, including Bauer BG-40, the most powerful of its kind in the Far East, were employed to ensure the stability of the bridge's foundations. Self-compacting concrete was used extensively to construct the piers and pylons. This type of concrete flows under its own weight, filling formwork and encasing reinforcements without the need for mechanical vibration, thereby improving the quality of the reinforced concrete structures. Additionally, the pylons' construction employed custom-made self-climbing formwork, allowing the bridge to be erected in 4.5-meter sections. This technology not only reduced construction time, but also enhanced structural integrity. The bridge's main span is supported by stay cables that are connected to the pylons, which taper as they rise from the base to the top. The pylons feature a variable cross-section, with the lower portion designed to bear the maximum load. High-grade concrete with a higher density than standard concrete was used for the pylon bodies to ensure the structure's robustness. The stiffening girder, which extends 1,244 meters, is an all-metal design with an aerodynamic profile to minimize wind load. The girder is composed of 103 panels, each weighing thousands of tons, which were pre-assembled at facilities on the Nazimov Peninsula and near Russky Island. These panels were then transported by barge to the bridge site and lifted into place using cranes at an elevation of 76 meters. To position the barge accurately, the GLONASS satellite navigation system was used, demonstrating the integration of advanced technologies in the construction process. The stay cable system is engineered for superior performance and efficiency. The cables consist of 13 to 79 strands, each made from 7 galvanized steel wires. The cables are covered with a high-pressure polyethylene jacket, which protects against corrosion and ensures the cable's long-term durability. The aerodynamic profile of the stay cables and the bridge girder helps reduce wind load by 25 to 30%, lowering material costs and improving the bridge's resilience to gusts. To further ensure the bridge's stability, the scale model of the bridge was tested in a wind tunnel. The findings from these tests informed the final design, ensuring that the bridge could withstand even the most severe wind conditions. The Russky Island Bridge is more than just a transportation link. It has become a symbol of Vladivostok's development and a source of pride for Russia. The bridge's sleek design and record-breaking dimensions have made it an iconic structure, drawing international attention. It is a popular destination for visitors, including government officials, foreign delegations, and tourists, who come to marvel at this modern engineering wonder. Upon the completion of construction, the temporary viewing platforms used during the building phase were transformed into permanent observation decks, allowing visitors to appreciate the breathtaking views of the eastern Bosphorus Strait and the surrounding area. The Russky Island Bridge stands as a testament to modern engineering and Russia's ambitions to establish Vladivostok as a gateway to the Asia-Pacific. The bridge not only connects the mainland to Russky Island, but also represents a link between Russia's past and its aspirations for the future. Its construction required overcoming numerous challenges, including extreme weather and complex logistics, but the end result is a bridge that is both functional and iconic. The project's successful completion in time for the 2012 APEC summit highlighted Russia's ability to execute large-scale infrastructure projects, even in challenging conditions. Today, the bridge serves not only as a crucial part of Vladivostok's transportation network, but also as a landmark that defines the city's skyline, symbolizing progress, innovation, and connectivity. The SEPSA beam launcher represents a specialized approach in the construction industry. Designed to streamline the installation of precast, prestressed concrete beams, this technology plays a crucial role in the development of large-scale infrastructure projects such as bridges, highways, and multi-story buildings. The use of specialized machinery not only enhances efficiency but also improves safety and precision during the construction process. The importance of precast prestressed concrete beams are widely used in construction due to their durability, strength, and ability to span long distances without intermediate supports. These beams are fabricated in a controlled environment where high-strength concrete and steel strands are combined to form a robust structural component. The prestressing process involves tensioning the steel strands before the concrete hardens, allowing the beams to better withstand tensile forces and reduce cracking under heavy loads. This makes them ideal for supporting large structures such as bridges, overpasses, and commercial buildings. However, the size and weight of these beams present significant logistical challenges during transportation and installation. This is where the SEPSA beam launcher comes into play, offering a sophisticated solution for handling and positioning these massive structural elements. The SEPSA beam launcher is a purpose-built piece of equipment designed to lift, transport, and install precast concrete beams with high precision. It is specifically engineered to handle the demands of heavy construction projects, where conventional cranes may not be suitable due to space limitations or the sheer weight of the beams. The launcher operates by utilizing a series of hydraulic systems and mechanical components that allow it to lift beams into place with minimal manual intervention. The process begins with the launcher positioning itself along the construction site, typically on a bridge or elevated roadway where the beams are to be installed. The machine then lifts the beam from a delivery vehicle and transports it horizontally to the desired location. Once in position, the launcher carefully lowers the beam onto its supports, ensuring proper alignment. This method significantly reduces the risk of accidents and structural damage, as the beams are moved and positioned with controlled precision. Efficiency. The SEPSA beam launcher accelerates the beam installation process, allowing construction projects to progress faster. By minimizing the need for multiple cranes and manual labor, the launcher optimizes workflow and reduces project timelines. Safety. Working with heavy precast beams poses risks, especially when using traditional lifting equipment. The SEPSA beam launcher's design prioritizes safety by reducing manual handling and the number of lifts required. It offers stability and control, minimizing the chances of accidents. Cost effectiveness. Although the initial investment in specialized machinery may be higher, the long-term savings are significant. Faster installation times and reduced labor costs contribute to lower overall project expenses. Versatility. The launcher can be adapted to various project requirements, making it suitable for different beam sizes and types. This flexibility allows construction companies to handle diverse projects using a single piece of equipment. The Northern Marmara Motorway is a significant infrastructure project that serves as a vital transportation link around Istanbul, providing an alternative route to alleviate traffic congestion in the city. As part of its construction, advanced engineering techniques, such as the incremental launching method, ILM, were employed to build several of its viaducts. This method, also known as the moving road, enables efficient and safe construction of long-span bridges and viaducts over challenging terrain. The incremental launching method involves building the bridge deck in segments in a casting yard located behind one of the abutments, bridge supports. These segments, typically measuring between 15 to 30 meters each, are cast in sequence. Once a segment is completed and the concrete has gained sufficient strength, it is pushed, or launched, forward along the supporting piers toward its final position. This process continues incrementally until the entire length of the bridge is constructed. The technique minimizes the need for large scaffolding or false work, which would be difficult to implement over obstacles such as rivers, highways, or deep valleys. The ILM is particularly well suited for projects like the Northern Marmara Motorway, which traverses diverse landscapes, including hilly areas and deep valleys. The method not only reduces the environmental impact by minimizing the use of temporary structures, but also improves safety by keeping most construction activities on the ground level. Prestressed, a leading civil engineering company specializing in bridge construction, successfully utilized the incremental launching method on the V17, V6, and V14 viaducts along the motorway. These viaducts are situated near the Third Bosphorus Bridge, an essential part of the Northern Marmara Motorway network. The technique allowed for the efficient construction of these long and high viaducts while maintaining strict quality and safety standards. The application of the incremental launching method on the Northern Marmara Motorway has been instrumental in ensuring that the motorway's construction could progress with minimal disruption to the surrounding environment and existing roadways, showcasing the method's advantages in modern bridge engineering. The installation of the final bridge girders at the Ridgefield National Wildlife Refuge marked a crucial step in a challenging construction project. The project involves setting the girders in two distinct sections. The first section, from Pier 1 to Pier 3, extended over the river, while the second section, from Pier 3 to Abutment 2, spanned the BNSF railway tracks. The installation process required cranes capable of lifting and placing the large girders in precise positions while maintaining stability over challenging terrain. To meet these demands, Secanti and Ness Campbell utilized a combination of the Manitowoc MLC 300, Liebherr LTM 1500, and Grove GMK 5275 cranes, each selected for their unique capabilities. The Manitowoc MLC 300, a 330-ton crawler crane, was an ideal choice for the job due to its high lifting capacity and flexibility. Its heavy-duty design and innovative variable position counterweight (VPC) system allowed it to handle the significant weight of the girders while reducing ground pressure. The VPC system automatically adjusts the crane's counterweight position to optimize stability and lifting performance, which was particularly beneficial when positioning the girders over the river. With its robust performance and versatility, the MLC 300 played a key role in lifting the girders from the staging area and setting them over the river section. Meanwhile, Ness Campbell's Liebherr LTM 1500, a 600-ton all-terrain mobile crane, provided the reach and power needed for the installation over the railway. The LTM 1500's telescopic boom, which can extend up to 84 meters, 275 feet, offered the necessary height to position the girders across the tracks, ensuring the bridge sections were aligned correctly. The crane's all-terrain mobility was advantageous for navigating the uneven ground near the railway. Additionally, the Grove GMK 5275, a 275-ton mobile crane, provided crucial support for positioning and securing the girders. Its compact design and strong lifting capabilities enabled it to assist with the installation in areas where space was limited, working in tandem with the larger cranes to ensure the girders were placed accurately and safely. The Sumner Bridge project is progressing smoothly, with significant construction milestones recently achieved. A key phase of the project took place on the night of March 20th, when crews set the bridge girders in place. This challenging task required shutting down Highway 410 overnight to ensure the safety of both workers and the public. The girders, each measuring 138 feet in length and weighing a staggering 125,500 pounds, nearly 63 tons, were carefully lifted and placed into position using specialized cranes. The nighttime operation was chosen to minimize traffic disruptions and maximize safety during the complex maneuver of setting these massive structural components. Positioning the girders marked a crucial step in forming the bridge's superstructure, providing the main horizontal support that will carry the future deck and traffic. The girder's placement represents the culmination of meticulous planning and engineering coordination, as each beam had to be precisely aligned to ensure the bridge's integrity and load-bearing capabilities. The next major milestone occurred on April 17th, when crews poured the concrete for the bridge deck. This phase involved laying the concrete atop the newly installed girders, forming the surface that will eventually support vehicles and pedestrians. The deck pour was a precise process that required careful timing, as the concrete needed to be evenly distributed and properly cured to achieve the necessary strength and durability. Pouring the deck not only adds structural stability, but also gives the bridge a more complete appearance, transitioning it from a skeletal framework of girders to something that genuinely resembles a finished bridge.